Welcome to the third part of our unit on electric potential. In this portion, we're really going to focus in on the potential and the field. How do these two things relate to each other? So I'm going to again go back to the definition of work. So remember, work is force times distance times cosine of theta, which is charge times field times distance times cosine of angle, which I can now write as charge times voltage or electric potential times a cosine. Okay. And that cosine is really important, because if the cosine is 0, I'm moving with the field. If the cosine is, let me repeat that. If the angle is 0, then I'm got a cosine of 1 and I'm moving with the field. And if the angle is 90, then the cosine is 0 and I am moving perpendicular to the field. And if I'm moving perpendicular to the field, then the work I'm doing is 0 and I have no change in energy, no change in voltage. So in order to get a change in voltage, I have to move parallel to the field. Okay. I mentioned this in the last section, but if we have a point charge, let's make it a positive point charge with the electric field pointing out everywhere, and I want to find lines of constant potential, then what I have to do is make sure that the potential lines are always perpendicular to the field lines. It comes back to that cosine. If I'm not perpendicular to the field, then I have moved with the field, and because I have moved with the field, I have experienced a change in potential, a change in energy. Okay. So field lines and equipotential lines are always perpendicular to each other. We looked at a couple of these last section. We're going to look at some more of this section. So I'm going to bring up the same simulation. Actually, it's exactly where we left it last time. Let's start here and think about, what are the field lines doing? We have a positive charge and we have a negative charge. And remember how the field lines went from positive to negative? It kind of did this wrap around thing. So if we turn them on and look, and can you see? Can you imagine a little compass, not a compass, a protractor there measuring all these angles, and how every time a field line crosses an equipotential, we get this 90-degree angle. Notice also in the middle, remember, we go from a positive potential to a negative potential. So somewhere in the middle here, there's a 0. Is the field 0 at the same location? Let's reset, and instead of looking at two oppositely charged particles, let's look at two particles with the same charge. I'm going to turn the potential off for a moment, so we're only looking at the field. This line here is a drawing artifact and doesn't actually exist. But you can see in the middle the the 0 in electric field. If I turn on potential, is it going to 0 here? No, it is not. What we see is we have the individual rings surrounding each charge individually, but then at some point the potential becomes equal for the two. And we get this line, and then it goes out from there. I can do this for any number of charges. Let's look at one that is kind of near and dear to what we've been doing. If I look at a line of charges, and it gets kind of messy. So there's my line of negative charges, and if I put next to it a line of positive charges, look at how messy this is getting. Right? You can see the uniformness of the field. The other thing you can see, if I get rid of the field lines over the top, is look at what the potentials are doing. We have a positive potential here. We have a 0 in between and a negative potential over there, which is consistent with the example that I gave in the first section on conservation of energy. I'm going to reset this. What happens if I look at two charges that are not the same size? So if I have a positive charge and I look at, say, a negative charge, field lines are still going to go from one to the other. But potentials, if we look at it, you still have a region where you go to 0. You have to go from being a positive potential around the positive charge to a negative potential around the negative charge. There is this 0 still, but it's no longer centered between them. It's shifted towards the smaller charge. Okay, so we've looked at a bunch of potentials and what they look like. And now let me summarize why behind the differences we saw. So for potential, remember this is a scalar. Okay. We can get positive and negative values due to the source being a positive or a negative charge, but that's the only way. For field, this is a vector. And what really matters is direction. Do the directions of the individual contributions to the total electric field work to add to something or cancel each other out? What's going on? So, two questions to conclude. If the electric field is 0 at a point in space, must the potential be 0? So let's go with an easy example and remember why the electric field goes to 0 at that point. So what I'm going to start with is two positive charges equal in size. I'm going to go to the spot right smack dab in the middle of them. So remember, at this spot, if I call this one A and that one B, then the electric field from A will point out of A, and the electric field from B will point out of B. And so now I can write that the total field will be vector form EA plus EB. These are the same charges, both are the same magnitude. And as I said, the distance was halfway in between. Then what this will look like is KQ over R squared minus KQ over R squared, and that gives me my 0 for electric field. The question now is, will the electric potential also go to 0 at this spot? So now let's find total potential. V total is going to be the potential due to A plus the potential due to B. It's not a vector, so I don't need to worry about directions. I don't have any arrows. The potential due to A will be K times Q divided by R. The potential due to B will be K times Q divided by R, which is 2KQ over R. So if the electric field is 0, must the potential be 0? No, it must not. So now let's flip this question around. What if the potential is 0? Must the field be 0? Okay, so we saw in the simulation that to get the potential to go to 0, I have to be between two charges of the same size but opposite sign. Oh, let me restate that a little bit. Two charges of opposite signs If I want it to go to 0 at the point directly in the middle of them, then they must be the same size but opposite sign. So at this spot, right in between, a distance r from both of them, the total potential will equal 0. And that's because if I do VA plus VB, letting this one be A and this one be B again, V total equals VA plus VB. This is going to be KQ over R plus K times minus Q over R, or negative Q over R. And that sums up to 0 volts. So I've got a spot where the potential goes to 0. What is the electric field at this spot? Well, if I come here, EA will point to the right. EB will also point to the right, out of positive into negative. So E total will be again EA plus EB, which is going to be KQ over R squared plus KQ over R squared, which is 2KQ over R squared. And again, I have an answer of no. If the potential is 0, must the field be 0? The answer is no. Now you may be wondering, is it possible that these two things are both 0? Yes, certainly. There are spots where both potential and field are 0. And a good one to think about is if I go a good distance away from the source charge, so R is big, potential is KQ over R, field is KQ over R squared. If R is big, both of those are going to go to 0. So you can have them equal to 0 at the same point in space, but they don't have to be. This concludes this section. In the next section, we're going to work a bunch of examples involving the electric potential.